So if we have a mixture of gases in a container, then the partial pressure of a single gas is defined as the pressure that that gas would have if it was alone in the container. And so Dalton's law of partial pressures says that for a mixture of gases, the total pressure of all of them is just the sum of the partial pressures of each individual gas. And we can also define the mole fraction. The mole fraction is the ratio of the number of moles of a single component in a mixture to the number of moles in the entire mixture. And for ideal gases, the mole fraction can also be written in terms of the partial pressures. So if we have a mixture and then we have the substance 1, then the mole fraction of substance 1 will be the moles of that substance divided by the total moles in the mixture. Or if the substance is a gas, the partial pressure of that gas divided by the total pressure. So as an example, let's look at an experiment you can do to collect oxygen by collecting it over water. So we have this reaction, 2KClO3 decomposes into 2KCl plus 3O2. So over here we have the reactants in the fire, and then they decompose into the solid and the gas. So the O2 gas will travel across this tube into the water, and it will bubble up and then reach this space above the water. So this space above the water will have the O2 gas that was formed in this reaction, and also some water vapor, because the water here is always evaporating and condensing. And so the water vapor that's above this water here is equal to the vapor pressure of the water. And we'll talk more about vapor pressure in a later video. So let's say the gas has collected a total pressure of 754 torr, and it's at 22 degrees Celsius. And the gas that we collect also takes up a volume of 0.65 liters. And so we know the vapor pressure of water at this temperature is 21 torr. So what is the partial pressure of the oxygen in this gas collection? And what is the mass of KClO3 that was decomposed to get this much oxygen? So in the gas mixture over here, the O2 and the water vapor both contribute to the total pressure. So by Dalton's law of partial pressures, the total pressure is just the partial pressure of O2 plus the partial pressure of H2O, which is 754 torr. So solving for the partial pressure of O2, since the partial pressure of H2O is equal to the vapor pressure of water, or 21 torr, the partial pressure of O2 is 733 torr. And we can convert that to ATM, because we'll need it in the later steps, and that's 0.964 ATM. And if we want to find the mole fraction of O2, we just do its partial pressure, 733, over the entire pressure, 754. So the mole fraction is 0.972. So now to find the mass of KClO3, we need to do some stoichiometry. So first we need to find the moles of O2, and we can do that with the ideal gas law. Solving for n equals PV over RT. And so we plug in those quantities that were given to us. So the moles of O2 is 2.59 times 10 to the negative 2 moles. And then we do some stoichiometry using the molar ratio and then the molar mass of KClO3 to get 2.12 grams of KClO3 were decomposed to produce this much oxygen gas. So next we're going to talk about effusion, which is basically when a gas escapes through a tiny hole in the container. Say you have a balloon and you poke a hole in it with a needle or something. And so Graham's law of effusion says that the rate of effusion of a gas is inversely proportional to the square root of its molar mass. So basically this means that if a gas is heavier, it will effuse slower, and a lighter gas will effuse faster. So we can use this to compare the effusion rates of two gases. So say we want to compare the rates of effusion of hydrogen, H2, to uranium hexafluoride, UF6. Well, we can set up the ratio. The rate of H2 over the rate of UF6 is going to be equal to the square root of the molar mass of uranium hexafluoride over the square root of the molar mass of H2. And they're flipped because the proportion is inverse. So we plug the molar masses in, and we find that the rate of effusion of H2 is 13.2 times the rate of UF6. So, which is expected because hydrogen is much lighter than uranium hexafluoride. So it will effuse much faster. So all this time we're talking about gases, we talk about ideal gases, which are obviously different from real gases. So the kinetic molecular theory is a model that explains what we mean when we say an ideal gas. And there are four main points to this model. The first is that the individual particles of a gas are so small compared to the distances between them that we can say the particles have a volume of 0. So we ignore the size of the particles. And two, the particles are constantly moving around, and the collisions with the container is what actually causes pressure. And three, the particles exert no forces on each other, which is not true. There are various intermolecular forces between the gas particles, but we can ignore them. And four, the average kinetic energy of a gas is directly proportional to its temperature in Kelvin. So kinetic energy is just measures how fast things are moving. So things that are moving faster have a higher temperature. So this means the temperature in Kelvin is really just a measure of how fast these particles are moving. And so real gases behave closest to ideal gases at low pressure and high temperatures. Low pressure because at low pressures the volume is bigger, there's more space for the gas particles, and so the distances between the particles can be greater. And we remember in point 1 we said that the distances between them are great. So the more distance between the particles, the more accurate this point is in the ideal gas model. And at higher temperatures, the particles are moving around faster. And so the intermolecular forces that they exert on each other are not as big when they're moving really fast. And remember, we ignored those forces that the particles exert on each other. And lighter gases also behave closer to ideal gases than heavier ones, because remember, we assumed that the particles have 0 volume. So we ignored the size of the particles, so the lighter the size actually is, the more accurate the ideal gas model will be.